All right, so we're going to look first at biomolecules, and I posted the video Friday's work. You should take a look at it. It is posted on the YouTube channel. You guys can look at it, especially if you were absent, you came in late, whatever. So for the person that came in late, let me go ahead and recap what we've talked about so far. One, there is a project, the project update is in Jupyter. All right. A project update's in Jupyter. It's sent to your parents and you. Please read it. We've reversed some scheduling. Two, on Friday, we finished talking about biomolecules, correct? We looked at, let me remind you before we go on, since this is Monday, let's kind of recap. We have carbohydrates, the two that we looked at that were important, that you need to know, that are going to come back and bite you if you don't know it, are deoxyribose. It looks like this in its schematic form. You've made it. You've built it. You're remembering at this point, hopefully, that you have carbon, 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 carbon. There's an OH and H for each of these, except for this one. This one's O is right here. And there's an OH coming off of this as well. So hopefully what you remember is that we have this 1 prime, 2 prime, 3 prime, 4 prime, 5 prime for deoxyribose. And deoxy just means that at this carbon there's a missing oxygen. Then we looked at ribose. Again, simple structure, I think. We're again 1, 2, 3, 4, 5 carbons, same structure. The difference is there is no missing oxygen. I would get an index card, make sure I know that. We call this one ribose and this one deoxyribose. That'll be important when we start to talk about protein synthesis later this month. When we look at glucose, that was again with the oxygen. It's the pattern's repeated over and over. So 6 carbons this time, not 5. Still the little arm up, little guy with the arm up. 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, 6 prime. And that's glucose. That's going to be an important one, we said. So those were the 3 sugars. Monosaccharides, we called them monosaccharides. Saccharide means sugar. Mono means 1. So 1 unit of sugar. 1 unit of sugar. These are the big ones. There's fructose. There's galactose. There's a number of monosaccharides. Now we can link them together. If we link them in giant, and this should be all of this should be
You zoom into, is it monosaccharides or something?
Yeah, yes, it is monosaccharides. No, I cannot zoom in right now. I will post this, though. Please feel free to look it up. So we can link all these sugars together and make different polysaccharides. So this is a bunch of sugars, and they can branch off, and there's different kinds. There's polysaccharides. Now, if the monosaccharide is glucose and they're in big chains, then the polysaccharide is going to, then the polymer can be in animals, including you, something called glycogen. Now, the AP kids will have to know the structure. They'll have to know if it branches, the types of linkages and all that, but you don't have to worry about that. You just have to know that in animals, the stuff that most mammals, we put it in our liver. So we put this sugar away in our liver. It's just a storage form of sugar. It's to get it out of our blood. It's temporary, short term. Short term storage form of sugar. Is that clear? Yeah? All right. If it's glucose and it's in plants, now things get a little more complicated. In plants, you have something called cellulose, which we've mentioned before. You're writing on it. It's what we make paper out of. It is sugar. Literally, the stuff you're writing on is sugar. Wood, what you're sitting on is sugar. Cellulose is sugar. But it's just connected in a way that we can't eat it. Almost nothing can eat it. It can only be digested by certain bacteria and fungi. Nothing else can eat paper or wood, not even plants. Plants don't put the sugar into wood to eat. They do it for structure. It's the problem when they update things. They never... I don't know what that is. I have no idea what just happened. Did you see what I clicked? Well, whatever. This is strictly, cellulose is strictly for, oh, that's no good. Strictly for, still too big. Structure. Do you understand that? Do you understand this word, structure? It's only to support itself. That's all plants use cellulose for. So this is the tree stems, the tree trunk, the grass, the fibrous stuff of the grass is all cellulose. Are we all good with that? Someone need me to do anything? We're good? All right. So that's cellulose. That's plants. Now, there is some plants but don't plants need sugar for food? Yes, they do. They do use sugar for food. They make sugar for themselves. They don't make sugar for us. We steal it. Animals steal sugar from plants. Plants make sugar for themselves. They're making their own food. Is that clear? So plants, when they need to put away food, they put it away in something called starch. You've heard of starch, correct? It's in potatoes. They put it in their roots. Almost everything can eat starch. It's a food. We love starch. I love French fries, potato chips, rice. All that is starch. Yams. I don't like yams either, but still, a lot of people like it. Pasta, all that is starch. All that comes from the stored form of energy. This is the storage form of energy for plants. You must know that. So plants use sugar in two ways. Plants use sugar in two ways. One for structure, two for energy. Do we understand that? The structure is cellulose. The starch is for energy. You need to put that down somewhere and know it. Okay? You don't have to know the difference between starch and cellulose, except that you need to know that that's how they're used. Repeat what part? Well, it's written on the board, so I did. It's not one of those things that I just said. So if we look, it says cellulose is digested by certain bacteria and fungi only. I'm mentioning that because a lot of people think that termites eat wood. They do, but they're using bacteria to digest the wood. They can't break the wood down. So this is an exception, an energy exception. But other than that, cellulose is for structure. Does that make sense? Are we good? Cellulose is for structure in plants. That looks a little light to me. Does that look light to you? That's cellulose in plants? Huh. Weird. All right, whatever. Oh, I see. Are we good? Cellulose is for structure and starch is for energy. That's sugar. We're done. That's what you need to know about sugar. Now, we use ribose and deoxyribose, and so do plants, in DNA and RNA, but they're still sugars. They start off in photosynthesis. And cellulose, and these are the energy storage forms of. Now, there are some other forms of polymers of sugar we could talk about. We're not going to. All right. So if you see on a problem on the OST, them talking about some other storage form of, this is strike 2. All right? Strike two.
Wait, for
I don't-
everybody or just that table?
That they know what I'm talking about. This is strike two. Stop. Okay. That's all right. Just remember this when I'm moving chairs around, okay? Don't get upset. There's no reason to get upset. I hate when you guys get upset. All right. So now, when you have a lot of sugar and you need to put away sugar, animals and plants, it's not always sunny. There are winter days, so the sun goes away and the plants lose their leaves and they can't make any more sugar. Animals need to eat, and when they have to walk 20, 30 miles, when bears go to sleep for the winter, they don't really sleep, they hibernate, but it's not quite what a lot of people think. When animals don't have food, they need to go a long time without eating. Sugar is not a proper way of putting it away because we use it too fast. So we have to we have to eat more than we're using, and then we have to put it away. Now today, in our modern culture, we don't have to do that. You get hungry, you go to the store, you get some food, or you go to your kitchen. In the real world, which may come again, God help us all. In the real world, you have to put food away while you have it. You have to eat it while you have it. If you're hunting, if we were all a tribe somewhere back 5,000 years ago, hunting in the wilderness, right? Some of us are gathering nuts and fruits, and some of us are out hunting some deer. We have food. What do we do with it? It's too much. What do we do with it? How? There's no containers, no refrigerators. There's in the old. You can salt it to some extent if you have salt, but if you don't have salt, you're out of luck. So what you do is what? There's no containers. There's no container you can build 5,000 years ago. It's in the winter. It might last a little longer, but still going to rot. So what do? Eat it, and eat it until we can't eat anymore, and then eat some more. What's going to happen?
Get full.
And then what do we do with all that food?
Throw it up.
No. Okay, let's not throw it up. What do we do with all that extra energy?
Use it.
Assuming we don't use it because we're eating too much.
Store it, save it.
How? You know how. Use your mind.
Sleep.
When you eat too much, what happens? Okay, you poop. All right, you die is kind of extreme. All right, so let's say we're not going to eat till we die. Let's say we're not. Some of it what we're pooping is stuff we didn't digest. Let's assume we're talking about the food we digested. So we've eaten and digested the food, right? We've eaten too much. Okay, we're going to sleep. What is our body going to do with all that energy? We can't put it in the liver. The liver's full. It's full of glucose. What do we do with the extra?
Feed it to the animals. What?
No, it's in our body. What, are you going to cut your finger off? Give it to here. Here, chicka. What are we going to do? What does your body do with it? You know what your body... Oh my goodness, stop. Think. I know it's early, but think. You digest it. It's more energy than you can use. What do you do with it?
The particles in your body.
You turn it into fat.
Exactly.
That's not even close to what you said. So, anyways, you take in all that extra food goes into fat. That's really good for us. So in the spring and summer, when there's plenty of food, we eat. Every time we eat too much, we gain 30, 40 pounds. Get a nice belly, got fat all around our thighs, our bellies, our arms.
You could cut it off.
Oh my God.
Just stop asking questions.
Yeah, shh. So this is good news because we're going to have to go for months without finding a lot of food. It's called winter. So when winter comes, it's going to get cold. And we're not going to have a lot of food. You can't grow anything in the winter, at least not in the north.
So we don't have cold fat. I'm sorry.
I'm just gonna take it away. So we're gonna use the fat in two ways. We're gonna use the fat in two ways. First, obviously, it's for energy. So it's long-term storage. Those people that didn't eat enough died in the winter. That's it. That's why fat people were thought of as pretty for the longest time, most of our history as humans. You can go back and look at historical drawings and paintings. The bigger you were, the richer you were, the more likely you were to survive, so the more attractive you were. Only now when our society's changed because we have plenty of food. Now I'm not talking about obese, right? Because 600 pounds, 700 pounds, it's not only is it not healthy, it still probably was attractive to people back then to some extent because you had to have a lot of money to get beat up big. Yeah.
So would you live, like what would you do if you was living in the forest like during the winter and you had nowhere to go?
Say what?
What if you was living in the forest during the winter? What would you do? Like would you like the animals like raw?
Oh my God. I would survive by hunting, gathering. I would start a fire and cook. I'd build a little cabin or at least a hut to protect me from the rain. I would pick high ground so when it rained, it wouldn't turn my bed into a swamp. I would likely make tools. I would learn how to fish with whatever I could find. You can take strips of meat, make it into threads. Hair especially, you can weave hair into threads. So as you skin the beast, you can take their hair and keep weaving it into a long thread that you can use then for fishing. Or you can spear fish, which works as well. The other thing that helps, of course, you would use the animal skins during this time as well, is thermal protection. In the winter, it's going to be cold, and there's not a God-blessed child in this room, including myself, that's going to walk out in the snow barefoot and naked and last for very long at all. Most of us would die very quickly in the cold. We would layer clothes on ourselves, clothes that we made during the spring and summer, clothes that would hopefully last us through the winter. We put boots on that are made of animal skins as well. And we would hopefully have this extra thermal protection of fat. Fat keeps us warm in the winter. So those two reasons fat are important. Also, fats are part of a group of nonpolar molecules. Now, what we mean by that, and I've discussed it before, is when we have two atoms that are sharing electrons like oxygen gas, O2 gas. Oxygen gas is nonpolar because these two atoms 1 and 2, are sharing electrons evenly. However, when atoms bond in a way, that same oxygen atom, but instead of being bonded to another oxygen, has two bonds to hydrogen, we call this water, H2O, liquid. It's liquid at room temperature. That's an L. Oxygen is stronger. It's able to pull the electrons more. So it pulls the electrons towards it more. It pulls the electrons towards it more. And because it's pulling the electrons, see the arrow? Does everyone see the arrow? Yeah. Okay. That makes oxygen partially charged. You see this little symbol means delta. Partially charged with a negative because it has the electrons more. It has more of the electrons more often. That's a Greek letter. That is a Greek letter, delta. Looks like an S with a little, or a snake or whatever you want to call it. It's a symbol called delta. It's a Greek letter. It's negative. And this other one on this side is delta with a positive. So it's partial charge. Partial charge. So this molecule of water gets the best of both worlds. It gets to share electrons, and oxygen gets the electrons more often, so it's happier. There are real big reasons why. By the way, before you go, add this word, polar molecule. And I got to say, you guys did really wonderfully once you settled down. You did a good job today. Asking questions, participating. I really like it. Please keep it up.